Welcome to the chapter Real Numbers.
This slide presents the overview of the chapter.
Learning objectives. By the end of this chapter, you will be able to identify rational and irrational numbers, state fundamental theorem of arithmetic, explain decimal expansions, prove irrational numbers, state laws of logarithms.
Introduction. Before entering into the chapter, follow the instructions shown on the screen. Click each tab to know more.
We learned from previous classes that natural numbers are the set of numbers which start from 1. They are denoted by n. Example: n is equal to 1, 2, 3, so on. Whole numbers are the set of numbers that include 0 along with the natural numbers. They are denoted by W. Example: 0, 1, 2, 3, and so on. An integer is a whole number that can be positive or negative or 0, but it should not be a fractional number. It is denoted by letter Z. For example, Z is equal to -3, -2, -1, 0, 1, 2, 3, and so on. Now, let us recall about rational and irrational numbers. Rational numbers are the numbers that can be expressed in the form of p by q, where p and q are integers and q not equal to 0. They are denoted by q. Always, rational numbers are expressed by using terminating decimals or non-terminating repeating decimals. Examples of rational numbers are as shown on the screen. Finally, we conclude that rational numbers contain the set of natural numbers, whole numbers, and integers. We also have irrational numbers which cannot be expressed in the form of p by q, where p, q are integers and q not equal to 0. Some of these numbers are √2, √3, and mathematical quantities like pi. When these are written as decimals, they are non-terminating and non-recurring. You know that rational numbers contain the set of natural numbers, whole numbers, and integers. But do you know that rational numbers are contained in some other set of numbers? Let us learn about various properties of rational and irrational numbers in details, and also about logarithms. Let us know about Euclid's division algorithm. The algorithm name itself suggests us to do with divisibility of integers. It simply states that if any positive integer x is divided by another positive integer y, then it gives remainder z which is smaller than y. Let us do an example. Suppose if x is equal to 22, y is equal to 5, then the remainder z equal to 2, which is smaller than y. The result obtained by division process is quite easy to understand, but it has got many applications relating to divisibility properties of integers. Let us learn few of them which are mainly used to calculate HCF of two positive integers. Now, let us learn about Euclid's division lemma by considering a puzzle. A trader was moving along a road by selling cups. An idler who did not have much work to do started to get the trader into a wordy duel. This grew into a fight. He pulled the basket with cups and dashed it on the floor. The cups broke. The trader requested the panchayat to ask the idler to pay for the broken cups. The panchayat asked the trader how many cups were broken. He gave the following response. If counted in pairs, 1 will remain. If counted in threes, 2 will remain. If counted in fours, 3 will remain. If counted in fives, 4 will remain. If counted in sixes, 5 will remain. If counted in sevens, nothing will remain. My basket cannot accommodate more than 150 cups. How many cups were there? Let us try to solve the puzzle and find how many cups were there in the basket. Solution. Let the number of cups be A. From the given problem, if we observe it from the last, we can say that A less than or equal to 150. Since the basket can accommodate either 150 cups or less than 150 cups, but not more than that. 1. If A is divided by 2, 3, 4, 5, 6 each time, then we know that the remainder in each case is 1 less than the divisor. That is, A is 1 less than the LCM of 2, 3, 4, 5, 6. Now LCM of 2, 3, 4, 5, 6 is 60. Therefore, A can be 60 minus 1, 120 minus 1, 180 minus 1 and so on. 2. If A is divided by 7, nothing will left given. That is, A is divisible by 7. 60 minus 1, that is 59, is not divisible by 7. 120 minus 1, that is 119, is divisible by 7. Therefore, A can be 119. 3. The trader basket cannot accommodate more than 150 cups. Therefore, 180 minus 1 cups cannot be there. Therefore, number of cups broken is equal to 119. To understand the Euclid's division lemma more clearly, let us do the problem by considering following pair of integers. A. 28. B. 17, 5. Consider a bit that is 20 and 8. Here A is equal to 20, B is equal to 8. Thus, by applying the Euclid's division lemma EDL to the above numbers, we obtain as follows. Here we know that A is equal to BQ plus R. So when 20 is divided by 8, we obtain quotient Q as 2 and remainder R is equal to 4. Substituting the obtained values of Q and R in the above expression, we obtain both LHS and RHS equal. Similarly, let's consider second set of numbers 17 and 5. Here, A is equal to 17, B is equal to 5. Thus, by applying the Euclid's division lemma EDL to the above numbers, we obtain as follows. Here we know that A is equal to BQ plus R. So when 17 is divided by 5, we obtain quotient Q as 3 and remainder R is equal to 2. Substituting the obtained values of Q and R in the above expression, we obtain both LHS and RHS equal. Sir, in Euclid's division lemma, the term lemma sounds differently. I never heard about it. Lemma is the typical word to hear and pronounce, but it is just a result. It is used in proving the other theorems. Suppose one wants to compute the HCF of two numbers. The most common method used is factorization. But to compute the factorization of large numbers such as 65,842, 24,895 and so on is very difficult and takes a lot of time. So Euclid has came up with a theorem that would help us to find the factorization method easily in less time. This theorem is very simple and is just another form of divisibility rule, which we have studied in our lower classes. Sir, could you please explain us the theorem of Euclid's? Okay, listen to the theorem statement. Now, let us know theorem on Euclid's division lemma. Statement: if a and b are two positive integers, then there exists unique whole number q and r, such that a is equal to bq plus r, where 0 less than or equal to r is less than b. Do you remember the divisibility theorem? Dividend is equal to divisor into quotient plus remainder. The Euclid's division theorem is originated from this. Sir, but how is it possible to use this theorem to find HCF? Can you please explain us more clearly in simpler way by taking few examples? To understand more clearly, first let me explain the theorem by an algorithm, step-by-step manner and flowchart. Algorithm. An algorithm is a step-by-step procedure or formula for solving a problem. The word algorithm has come from the name of the Persian mathematician Al-Khwarizmi, earlier transliterated as algorithm or algorithm. The word algebra is also derived from a book which he has written called Hisab al-Jabr wal-Muqabala. Euclid's division algorithm is used to compute the highest common factor, HCF, of two given positive integers. To obtain the HCF of two positive numbers, say a and b, follow these steps. Step 1. Apply Euclid's division lemma to a and b. So there exists whole numbers p and r such that a is equal to bp plus r, where 0 less than or less than b. Step 2. If r equal to 0, b is the HCF of a and b. If r is not equal to 0, then apply division of lemma to b and r. Step 3. Continue the same process until the remainder is 0. The divisor that is obtained at this stage is the required HCF. Flowchart. Here let us know sequentially in the flowchart to keep the steps to find the HCF. Let the first number be a and second number be b. If a is greater than b, then according to Euclid's division, lemma a is equal to bq plus r, where q and r integers and 0 less than or equal to or less than b. Suppose a is equal to bq plus r. If r is equal to 0, then b is the HCF of positive numbers a and b. If a is equal to bq plus r, if r not equal to 0, we apply the division lemma to b and r and continue the process till the remainder becomes 0. If a is less than b, then according to Euclid's division, lemma b is equal to aq plus r, where q and r are integers and 0 less than or equal to r less than a. In b is equal to aq plus r. If r is equal to 0, then a is the HCF of positive numbers a and b. In b is equal to aq plus r. If r is not equal to 0, we apply the division lemma to a and r and continue the process till the remainder becomes 0. Now, let us do some examples by taking small numbers first and then large numbers. To understand the Euclid's division lemma more clearly, let us find the HCF by considering following pairs of integers. A. 24. Step 1. Apply EDL to the above numbers. Here A is equal to 20, B is equal to 4. Substitute the values in A is equal to BQ plus R. So when 20 is divided by 4, we obtain quotient Q as 5 and remainder R is equal to 0. Substituting the obtained values of Q and R in the above expression, we obtain both LHS and RHS equal. That is 20 is equal to 4 into 5 plus 0. As the remainder is 0, the process stops. The divisor at this stage is 4. Therefore, HCF is equal to 4. B. 4032, 262. In the given pair, 4032 is greater than 262. Therefore, let A is equal to 4032 and B is equal to 262. Step 1. By applying EDL relation A equal to BQ plus R, where 0 less than or equal to B less than R, we get as shown. So, 4032 is equal to 262 into 15 plus 102. As R equal to 102, which is in turn not equal to 0. Now apply Euclid's division lemma to 262 and 102. Step 2. (262) is equal to 102 into 2 plus 58. As R is equal to 58, which is not equal to 0. Apply Euclid's division lemma to 102 and 58. Step 3. (102) is equal to 58 into 1 plus 44. As R is equal to 44, which is not equal to 0. Apply Euclid's division lemma to 58 and 44. Step 4. Here 58 is equal to 44 into 1 plus 14. As R equal to 14, it is not equal to 0. Apply Euclid's division lemma to 44 and 14. Step 5. (44) is equal to 14 into 3 plus 2. As R equal to 2, it is not equal to 0. Apply Euclid's division lemma to 14 and 2. Step 6. (14) is equal to 2 into 7 plus 0. Since the remainder is 0, the process stops. The divisor at this stage is 2. Hence, HCF is equal to 2. Euclid's division lemma or algorithm has several applications in order to find the properties of numbers. Let us do some examples. Show that every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1, where q is some integer. Solution. Let a be any positive integer and b is equal to 2. By Euclid's algorithm, a is equal to 2q plus r for some integer q greater than or equal to 0 and r equal to 0 or r equal to 1. 1. For r equal to 0. A is equal to 2q. 2. For r equal to 1. A is equal to 2q plus 1. If a is of the form 2q, then a is an even integer. If a is of the form 2q plus 1, then a can be any positive odd integer. Two. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. Solution. Let a be any positive integer and b equal to 6. By substituting the value of b in EDL a equal to bq plus r, we get a equal to 6q plus r, where 0 less than or equal to or less than 6. Now, by substituting r equal to 0 in equation 1, we obtain a equal to 6q. By substituting r equal to 1 in equation 1, we obtain a equal to 6q plus 1. By substituting r equal to 2 in equation 1, we obtain a equal to 6q plus 2. By substituting r equal to 3 in equation 1, we obtain a equal to 6q plus 3. By substituting r equal to 4 in equation 1, we obtain a equal to 6q plus 4. By substituting r equal to 5 in equation 1, we obtain a equal to 6q plus 5. Solving the above equations for a, we obtain a is equal to 6q or 6q plus 1 or 6q plus 2 or 6q plus 3 or 6q plus 4 or 6q plus 5. From equation 2, 6q, 6q plus 2, 6q plus 4 are the even integers. 6q plus 1, 6q plus 3, 6q plus 5 are the forms of any positive odd integer. Verification. Assume any value of q such as 1, 2, 3, 4, so on up to n. Substituting the values of q in equation 2.2, we get if q equal to 1, then 6q plus 1 is equal to 6 into 1 plus 1, which is equal to 6 plus 1, that is 7, which is a positive odd integer. 6q plus 3 is equal to 6 into 1 plus 3, which is in turn equal to 6 plus 3, that is 9, which is a positive odd integer. 6q plus 5 is equal to 6 into 1 plus 5, which is in turn equal to 6 plus 5, that is 11, which is a positive odd integer. If q equal to 2, then 6q plus 1 is equal to 6 into 2 plus 1, which is in turn equal to 12 plus 1, that is 13, which is a positive odd integer. 6q plus 3 is equal to 6 into 2 plus 3, which is in turn equal to 12 plus 3, that is 15, which is a positive odd integer. 6q plus 5 is equal to 6 into 2 plus 5, which is in turn equal to 12 plus 5, that is 17, which is a positive odd integer. Similarly, for different values of q, we obtain the result as a positive odd integer. Problem 3 is that use Euclid's division lemma to show the cube of any positive integer is of the form 9m, 9m plus 1, or 9m plus 8. Solution. Let a be any positive integer and b equal to 3. Substituting the value of b in Euclid's division, lemma a equal to b cube plus r, we get a is equal to 3 cube plus r, where 0 less than or equal to or less than 3. Let it be equation 1. Case 1. If r equal to 0, then a equal to 3 cube, that is equation 1.1. By cubing equation 1.1 on both sides, we get a cube is equal to 3q cube, which is equal to a cube equal to 27q cube. That is in turn equal to a cube equal to 9 into 3q cube. That a cube is equal to 9m, where m equal to 3q cube, that is equation 1.1.1. Case 2. If r equal to 1, then a is equal to 3q plus 1. By cubing equation 1.2 on both sides, we get a cube is equal to 3q plus 1 whole cube. As it is in the form of a plus b whole cube, we write it as shown. Now, by further solving, we get a cube is equal to 9m plus 1. Let us represent it as equation 1.2.1, where m is equal to 3q cube plus 3q square plus q. Case 3. If r equal to 2, then a is equal to 3q plus 2. By cubing equation 1.3 on both sides, we get a cube equal to 3q plus 2 whole cube. As it is in the form of a plus b whole cube, we write it as shown. Now, by further solving, we get a cube is equal to 9m plus 8. Let us represent it as equation 1.3.1, where m is equal to 3q cube plus 6q square plus 4q. Thus, from the obtained result in 3 cases, we can say that the cube of any positive integer will be of the form 9m, 9m plus 1, 9m plus 8. (4) Show that the square of any positive integer is either of the form 4m, 4m plus 1 for some integer m. Solution. Let a be any positive integer and b is equal to 4. By substituting the value of b in Euclid's division, we obtain a is equal to 4q plus r, where 0 is less than or equal t or less than 4. The possible reminders are r equal to 0, 1, 2, 3. Case 1 for r equal to 0. A is equal to 4q plus 0, that is a equal to 4q. By squaring equation 1.1 on both sides, we obtain a square is equal to 16q square is equal to 4q square. This is in the form of 4m, where m is equal to 4q square. Case 2 for r equal to 1. A is equal to 4q plus 1. By squaring equation 1.2 on both sides, we obtain a square is equal to 4q plus 1 whole square, which is equal to 16q square plus 8q plus 1, which is in turn equal to 4 into 4q square plus 2 plus 1. This is in the form of 4m plus 1, where m is equal to 4q square plus 2. Case 3. For r equal to 2, a is equal to 4q plus 2. By squaring equation 1.3 on both sides, we obtain a square is equal to 4q plus 2 whole square, that is equal to 16q square plus 16q plus 4, which is in turn equal to 4 into 4q square plus 4q plus 1. This is in the form of 4m. Let it be represented as equation 1.3.1. Case 4. For r equal to 3, a is equal to 4q plus 3. by squaring equation 1.4 on both sides, we obtain a square is equal to 4q plus 3 whole square, which is in turn equal to 16q square plus 24q plus 9, which is equal to 4 into 4q square plus 6q plus 2 plus 1. This is in the form of 4m plus 1. Let it be represented as 1.4. Exercise problem. Let us solve exercise problem. You can click Solution tab to verify your answer.
Let us solve a few exercise problems. Click the tab to view solution.
Let us see a discussion between Raju and Rajesh about real numbers. Rajesh, are all integers also included in real numbers? Why? Yes, Raju, I will explain you by taking a number line here. The real numbers are the set of numbers containing all of the rational numbers and all of the irrational numbers. All the integers are included in the rational numbers, since any integer z can be written as the ratio z by 1. The real numbers are all the numbers on the number line. There are infinitely many real numbers, just as there are infinitely many numbers in each of the other sets of numbers. But it can be proved that the infinity of the real numbers is a bigger infinity. Thanks, Rajesh, for explaining the topic. Exploring real numbers. Click each tab to know more. Let us first know about prime numbers and composite numbers. Prime number. A prime number is any number greater than 1 and has exactly two factors, 1 and itself. For example, the numbers 2 and 3 are prime numbers since they have factors 1 and itself. Some more prime numbers are 5 and 7. And the number 4 is not a prime number since it has more than two factors as 1, 2, 4. Some more examples which are not primes are as shown on the screen. Composite numbers. Composite numbers are the numbers which have more than two factors, that is the number 1, the number itself, and at least one other number. Examples are as shown on the screen. Note: 1 is neither prime nor composite. We know that all natural numbers except 1 can be written as a product of their prime factors. For example, let us go through some of the numbers. Say 3 is equal to 1 into 3. 6 can be written as 2 into 3. 253 can be written as 11 into 23, and so on. But here 1 is neither a composite nor a prime. Can there be a composite number that isn't the product of the powers of primes? For this, let us take an example of factorizing a large natural number 163800. Let us use factor tree that is well familiar to all. Now, let us have a look on some of the natural numbers. 163800 can be written as 2 into 81900, and 81900 can be written as 2 into 40950. 40950 can be written as 2 into 20475, can be written as 3 into 6825. 6825 can be written as 3 into 2275. 2275 can be written as 5 into 455. 455 can be written as 5 into 91 and 91 can be written as 7 into 13. Here factorization of 163800 as shown. Therefore, when we write the above terms in terms of product of powers of primes, we obtain as shown. Let us try with another number. 1, 2, 3, 4, 5, 6, 7, 8, 9. This can be written in the following form as shown. Here the numbers 3803 and 3607 are primes. By this we can prove that a composite number can be written as the product of primes. Here are some examples as shown on screen. If the numbers taken has all the possible primes, what would be the size of the collection? Will it contain only a finite number of primes or infinitely many? It is infinitely many. Therefore, if we multiply all these primes in every possible way, it produces an infinite collection of composite numbers. The following gives us the fundamental theorem of arithmetic that tells every composite number can be factorized as a product of primes or given any composite number. It can be factorized as a product of prime numbers in a unique way, except for the order in which the primes occur. Take an example for this. Take a number 210 and factorize it. We get product of 2, 3, 5, 7 as same as product of 3, 5, 7 and 2 or any other possible order. By this we conclude that there is only one way of writing the product of primes. Now, let us state the fundamental theorem of arithmetic. Exploring real numbers. Statement of fundamental theorem of arithmetic. Every composite number can be expressed or factorized as a product of powers of primes, and this factorization is unique, apart from the order in which the prime factors occur. Let x be the composite number. Let us factorize it as shown, where x is equal to p1, p2, pn are the primes. If we use same primes, we get all the powers of primes. When the primes are arranged in ascending order, we get it as p1 less than or equal to p2 less than or equal to, so on up to less than or equal to pn. Then the factorization number is unique. For example, 1,63,800 can be written in terms of product of prime factors as shown. Exploring real numbers. For example, the composite number 2310 is expressed in terms of product of primes as shown on the screen. Therefore, the products of primes are 2, 3, 5, 7 and 11. Now, let us learn how to apply the fundamental theorem of arithmetic on more than one positive number using the prime factorization method. Prime factorization method. This method involves finding the prime factors of a given number. This method is used to find the highest common factor HCF and the least common multiple LCM of the given number. Let us look at an example. Find HCF of integers 12, 18 by the prime factorization method. Solution. Consider the positive integer 12. To find its HCF, express it as a product of 2 and 6. Here 2 is a prime number and 6 is a composite number. Now, the composite number 6 can further be expressed as the product of two prime numbers 2 and 3. In this way, the number 12 is expressed as a product of prime numbers only. Similarly, the expression of other positive integer 18 in terms of product of primes is shown on screen. It is observed that the highest common factor of these three numbers is 6. Therefore, the HCF of the numbers 12, 18 is 6. That is equal to product of the smallest power of each common prime factors in the numbers. Find the least common multiple of 12 and 18. To find the least common multiple of the given numbers, consider the number 12 among the given numbers. It can be written as the product of least common multiple 2. The number 18 can be written as multiples of 2. The number 6 is further expressed as a factor of 2, keeping the other number unchanged. At this stage, the two numbers can be expressed as factors of the least multiple 3. Now, the obtained numbers are prime in nature. They cannot be further factorized in terms of numbers other than 1 and themselves. The product of all these prime numbers is shown on screen as the least common multiple of the given numbers is equal to product of the greatest power of each prime factors in the numbers. Consider the numbers 4 power n, where n is a natural number. Check whether there is any value of n for which 4 power n ends with the digit 0. The number 4 power n does not end with 0 because it should be divisible by 5 or should contain a prime number 5 in prime factorization. But it is impossible with this as 4 power n is equal to 2 to the power of 2n, so 2 is only prime in the factorization of 4 power n. As there is no number 5 as prime factor and there is no natural number n for which 4 power n ends with the digit 0. Show that 12 power n cannot end with the digit 0 or 5 for any natural number n. The number 12 power n does not end with 0 because it must be divisible by 5 or 10 and should contain a prime number 5 in prime factorization. But it is impossible with this as 12 power n is equal to 2 to the power of 2n into 3. So 2 and 3 are the only prime in the factorization of 12 power n. As there is no number 5 as prime factor and there is no natural number n for which 12 power n ends with the digit 0.
Let us solve a few exercise problems. Click the tab to view solution.
Knowledge check. Attempt the following questions to check your understanding. Classification of decimal numbers. Decimal expansion is classified into terminating and non-terminating. The non-terminating is further classified into repeating and non-repeating. Let us discuss each in detail. Let us know in detail about terminating decimals. The word terminate means end. A decimal that ends is a terminating decimal. In other words, a terminating decimal has a finite number of digits after the decimal point. Click each tab to know more. Let x be a rational number whose decimal expansion is terminating. Then x can be expressed in the form of p by q, where p, q are co-prime and the prime factorization of q is of the form 2 power n, 5 power m, where n, m are non-negative integers. Some of the decimal numbers expressed in p by q form are as shown on screen. By expanding this number further in the form of p by q, we get as follows. That is, writing the numerator and denominator in terms of the product of primes, we get as shown. Similarly, the terminating decimals 1.04 and 12.5 are expressed as follows. Any rational number that has a decimal expansion which terminates is expressed as a rational number whose denominator is a power of 10, where 2 and 5 are the only prime factors of 10. Therefore, during the simplification of rational number, we observe that the number is in the form of p by q, where the prime factorization is in the form of 2 power n, 5 power m and nm are non-negative integers. Let x is equal to p by q be a rational number, such that the prime factorization of q is of the form 2 power n, 5 power m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. For example, the rational number 26 by 25 is expressed as 26 by 5 square. Now the prime for both the numerator and the denominator are as shown. Thus by further solving, we get as 1.04. Similarly, the expansions of the other two rational numbers are as shown on screen. Now, let us solve an example problem on this theorem. The word non-terminate means never end. A decimal that never ends is a non-terminating decimal. Let us solve a few example problems on non-terminating decimals. For example, let us consider decimal conversion of 1 by 7, which is non-terminating and recurring decimal. By further solving, we can see that the decimal never ends and the remainders are not repeating. But as the quotient is repeating itself, it is denoted by a bar. Since denominator is 7, which is not of the type 2 power n, 5 power m. Let us consider one more example. Here, when the dividend 10 is divided by divisor 3, the remainder repeats itself. Also, a decimal number in the quotient repeats itself without termination. In this example, as 3 is repeating itself, hence it is non-terminating decimal. So, from the above two examples, let us state a theorem. Let x is equal to p by q be a rational number, such that the prime factorization of q is not of the form 2 power n, phi power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating. Example 3. Using the above theorems, without actual division, state whether the following rational numbers are terminating or non-terminating, repeating decimals. Solution. By the theorem, let x is equal to p by q be a rational number, such that the prime factorization of q is not of the form 2 power n phi power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating or recurring. Thus, by solving all the given rational numbers, we get as follows. Example 4. Write the decimal expansion of the following rational numbers without actual division. The decimal expansion of the following rational numbers is as follows. Now, attempt the following problems. You can click Answer tab to verify your answers.
Let us solve a few exercise problems. Click the tab to view solution.
Have a look at irrational numbers. A number is said to be irrational if and only if the number can't be written in the form of p by q, where p and q are integers and q naught equals to 0. These are the numbers which express a fraction into a decimal by the division method. Here, even if the division process continues indefinitely, a zero remainder is never obtained. These decimals never repeat and never terminate. Let us look into some examples that we are familiar with. We will also prove that root 2, root 3, root 5 and in general root p is irrational, p is a prime. Before proving, let us state and prove with the help of fundamental theorem of arithmetic. Consider the following theorem. Its statement is, let p be a prime number if p divides a square, then p divides a, where a is a positive integer. The proof of this statement is based on the fundamental theorem of arithmetic. Let a be a positive integer. Hence a is equal to p1, p2 till pn, where p1, p2 till pn are primes, not necessarily distinct. Therefore, a square is written as shown on screen. Now, we are given that p divides a square. Therefore, from the fundamental theorem of arithmetic, it follows that p is one of the prime factors of a square. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize that the only prime factors of a square are p1, p2, so on pn. So p is one of p1, p2 till pn. Now, since a is equal to p1, p2 till pn, therefore p divides a. Let us use this theorem to solve a sample problem. Verify the statement proved above for p is equal to 2 and p is equal to 5 and for a square is equal to 1, 4, 9, 25, 36, 49, 64 and 81. From the statement we proved that is, let p be a prime number. If p divides a squared, then p divides a, where a is a positive integer. During p is equal to 2 prime number, if 2 divides a square is equal to 4, 36, 64, then p divides a is equal to 2, 6, 8. During other cases, that is when a square equals to 1, 9, 25, 49 and 81, therefore the statement isn't correct. During p is equal to 5 prime number, if 5 divides a square is equal to 25, then p divides a is equal to 5. During other cases, that is when a square equals to 1, 4, 9, 25, 36, 49, 64 and 81. Therefore, the statement isn't correct. Prove that root 2 is irrational. Proof. Let us assume to the contrary that root 2 is rational. Then, we can find two integers p and q such that root 2 is equal to p by q, where p, q are integers and q not equal to 0. Suppose p and q have a common factor other than 1. Then we divide the number by the common factor to get root 2 is equal to a by b, where a and b are co-prime numbers. So, b root 2 is equal to a. By squaring on both sides, we get equation 1 as shown on the screen. Therefore, 2 divides a square. Now, from theorem 3, we can say that 2 divides a. Therefore, we can write a is equal to 2c for some integer c. Substitute the value of a in equation 1. We get 2. This means that 2 divides b square and so 2 divides b also. Therefore, a and b have 2 as a common factor. But this contradicts the fact that a and b are co-prime. This contradiction has arisen because of our incorrect assumption that root 2 is rational. So, we conclude that root 2 is irrational. Example. Show that 5 minus root 3 is irrational. Solution. Assume the given one is rational. So by the above statement, co-primes a and b not equals to 0 can be found such that, hence, rearranging the equation, as a and b are integers, we get. But this contradicts the fact that root 3 is irrational. This contradiction has arisen due to the wrong assumption that 5 minus root 3 is rational. Hence we conclude that 5 minus root 3 is irrational. Show that 3 root 2 is irrational. Assume the given one is rational. So by the above statement, co-primes a and b not equals to 0 can be found such that 3 root 2 is equals to a by b. Rearranging the equation, as a and b are integers, we get a by 3b is rational and therefore root is irrational. But this contradicts the fact that root 2 is rational. Hence we can say that 3 root 2 is irrational. Prove that root 2 plus root 3 is irrational. Solution. Assume the given one is rational. Let root 2 plus root 3 is irrational and a by b is irrational, b not equals to 0. Hence root 2 is equals a by b minus root 3. Squaring on both sides we get rearranging. Since a, b are integers, a squared plus b squared by 2ab is rational. This contradicts the fact that root 3 is irrational. Therefore, root 2 plus root 3 is irrational. Note that the sum of the two irrational numbers need not be irrational. For example, if a is equal to root 2 and b is equal to minus root 2, then both a and b are irrational. But a plus b equal to 0, which is rational. Next, the product of two irrational numbers need not be irrational. For example, a is equal to root 2 and b is equal to root 8. Then both a and b are irrational. But ab is equal to root 16, which is equal to 4, is rational.
Let us solve a few exercise problems. Click the tab to view solution.
Knowledge check. Attempt the following questions to check your understanding. The table shown on the screen is about different types of properties with respect to addition and multiplication, where a, b and c are any real numbers. Find whether the real numbers satisfy the listed properties or not. Let us know how logarithms are used in real life. Usage of logarithms is in calculations of engineering, science, business, economics, and also in calculating compound interest. Logarithms are used for all sorts of calculations in engineering, exponential growth and decay, pH value in chemistry, measurement of the magnitude of earthquakes, etc. Before going to learn about logarithms, we need to recollect laws of exponents. This is because logarithms and laws of exponents are closely related, and in order to understand logarithms, a good knowledge of laws of exponents is required. For example, in the given expression 4 is called the power or exponent, 3 is called the base. We know that any composite number can be expressed as product of powers of prime numbers. Suppose we want to multiply 27 with 81. One way is to multiply both the numbers directly. The other way is to use the rules of exponent. The product of 27 and 81 can be written as 3 power 7 according to the laws of exponents as shown on screen. Similarly, if we want to divide 81 with 27, we obtain the number 3 as per the laws of exponents. Therefore, for replacing multiplication with addition and for replacing division with subtraction of numbers in exponential form, logarithms are necessary. Now, let us know what a logarithm is. Writing exponents as logarithms. For example, 10,000 can be written as 10 power 4, where 10 is the base and 4 is the exponent. So, Writing a number in the form of a base raised to a power is known as exponentiation. We can also write it in another way called logarithms as log 10. 10,000 can be written as 4. This is stated as log base 10 of 10,000 equals 4. Thus, logarithmic form is expressed as shown. General case: if a power n is equal to x, then logarithmic form of it is log x to the base a equal to n, where a and x are positive numbers and a not equal to 1. Similarly, the exponential form of log x to the base a equal to n is a power n is equal to x. Example: the logarithmic form of 2 cube is equal to 8 is shown on the screen. Now, let us solve a sample problem on logarithms. Let us solve some example problems on logarithms. Write the logarithm form of 64 is equal to 8 square. Solution: recall that if a power n is equal to x, then its logarithmic form is log x to the base a equal to n. On comparing the given expression with the general form, we obtain the value of a, x and n as shown on the screen. So, its logarithmic form is log 64 to the base 8 equal to 2. Write the exponential form of log 25 to the base 5. Solution: recall that if log x to the base a is equal to n, then x is equal to a power n. On comparing the given logarithmic expression with the general form, we obtain the value of a, x and n as shown on the screen. So the base 5 on screen should be raised to the power of 2 to obtain the number 25. Determine the value of y in log 2 to the base 8 is equal to y. Solution: the exponential form of above logarithmic function is as shown on the screen. As 8 can be further expressed as 2 power 3, so we write it as shown. By further solving it, we get as follows. Thus y is equal to 1 by 3. Knowledge check. Attempt the following question to check your understanding. Write 10,000 in exponential form and identify its base and index. Here, as 1000 can be written as 10 to the power 4, where base is 10 and index is 4. Find product of 25 and 125 without actual multiplication using exponents. The solution is as 25 can be written as 5 square and 125 can be written as 5 cube. Thus, the product of 25 and 125 is equivalent to 5 power 5, which is in turn equal to 3125. Express 128 and 32 as powers of 2 and find 128 divided by 32. Solution: by factorizing 128, we get 2 power 7 and for 32 we get 2 power 5. Now, by dividing equivalent terms of 128 and 32, we get as shown. Write 16 equal to 2 to the power 4 in logarithmic form. Is it same as log 16 to the base 4? Given that 16 is equal to 2 power 4, it is same as log 16 to the base 2 equal to 4. But log 16 to the base 2 is not same as log 16 to the base 4. Because log 16 to the base 4 is equal to log 4 squared to the base 4, which is equal to 2. Show that a power 0 is 1. So log 1 to the base a is equal to 0. Since a power m by a power n is equal to a power m minus n, put n equal to m in equation 1. Then we get as follows. So the logarithmic form of a power 0 equal to 1 is log 1 to the base equal to 0. Logarithmic form of 11 square equal to 121 is. The given expression is in the form of a to the power x equal to b. We know the logarithmic form of a to the power x equal to b is expressed as log b to the base a equal to x. Therefore, the logarithmic form of the given expression is log 121 to the base 11 equal to 2. Given expression is log 2 to the base 2 equal to 1, which is in the form of log b to the base a equal to x. Since log b to the base a equal to 1 equal to a power x equal to b. Thus we write it as 2 power 1 equal to 2. Determine the logarithmic value of log root c to the base c is equal to z. Let log root c to the base c is equal to z. Then the exponential form is c power z equal to root c, z equal to 1 by 2. Now let us discuss the laws of logarithms in detail. There are three main laws of logarithm. They are first law, second law, and third law. Click each tab to know more. First law tells us how to add two logarithms together. Consider two exponents x is equal to a power n and y is equal to a power m. Their equivalent logarithms are log x to the base a equal to n and log y to the base a equal to m, which is represented as equations 1. Multiply x and y. We get the following expression as shown on the screen. Applying log on both sides, we get its logarithmic form is equation 2. By substituting 1 in 2, we get the first law of logarithm. Log xy to the base a is equal to log x to the base a plus log y to the base a. So, if we want to multiply two numbers and find the logarithm of the product, we can do this by adding the logarithms of the two numbers. This is first law of logarithms. Note that the logarithm of 1 to any base is always 0. Example, log 1 equal to 0. And the logarithm of a number to the same base is always 1. Example, log 10 to the base 10 is equal to 1 and log e to the base e is equal to 1. Now, let us solve a sample problem on this law. Example, expand log 15 to the base 10 using first law. Solution. We know log xy to the base a is equal to log x to the base a plus log y to the base a. Log 15 to the base 10 can be expressed as log 5 into 3 to the base 10. Applying the first law of logarithm on the given logarithmic expression, it can be expressed as shown on the screen. Now, Let us learn the second law of logarithm. Second law. Consider x is equal to a power n as equation 1. Its equivalent logarithmic form is log x to the base a is equal to n. If we raise both sides of equation 1 to the power m, the obtained expression is as shown. Applying the laws of exponents on this expression, we get another expression as shown on the screen. Its logarithmic form is log x power m to the base a is equal to nm is equal to m log x to the base a. This is second law. It states that the logarithm of a power of a number can be obtained by multiplying the logarithm of the number by that power. Let us solve an example problem based on the second law. Example: simplify log 5 cube to the base 10. Solution: applying the second law of logarithms, we obtain the results as shown on screen. Third law. Consider x is equal to a power n and y is equal to a power m as equation 1. Their equivalent logarithmic forms are log x to the base a is equal to n and log y to the base a is equal to m as equation 2. Now divide x with y. The obtained expression is shown on the screen. Applying the laws of exponents to the above equation and applying logarithms, we get as shown on the screen. From 2, we can write it as log x by y to the base a is equal to log x to the base a minus log y to the base a. This is third law. It states that if we want to divide two numbers and find the logarithm of the result, we can do this by subtracting the logarithms of the two numbers. Let us solve an example problem based on third law of logarithm. Example: expand log 18 by 65. The solution is as follows. As we know, log x by y to the base a is equal to log x to the base a minus log y to the base a. So we write the given expression as log 18 minus log 65. Now, let us solve some example problems based on all these three laws. Write log 10 plus 2 log 3 minus log 2 as a single logarithm. Initially, write the second term of the given expression in the form of third law as shown. Now, write the first two terms using first law as shown on the screen. Now, finally represent the above equation in terms of second law. Therefore, the single logarithm of the given expression is log 45. Now expand the expression log 343 by 125. The solution is as follows. If we know that log x by y to the base a is equal to log x to the base a minus log y to the base a. So log 343 by 125 is expressed as log 343 minus log 125. Since log x power m to the base a is equal to m log x to the base a, so the given expression is expressed as log 7 power 3 minus log 5 power 3, which is in turn equal to 3 log 7 minus 3 log 5. Therefore, log 343 by 125 is equal to 3 of log 7 minus log 5. Let us solve it as following. As all the three logarithmic expressions are in the form of m log x to the base a, so we write them in the form of log x power m to the base a as shown. This is in turn equal to log 9 plus log 125 minus log 32. Now observe the first two terms, it is in the form of log x plus log y, so let us write in the form of log xy as shown. Now the obtained expression is in the form of log x minus log y, so we write it in the form of log x by y. Thus, we get log 1125 by 32. Knowledge check. Attempt the following question to check your understanding. Since the given expression is in the form of log xy equal to log x plus log y, we can write it as shown on screen. Since log x by y is equal to log x minus log y, we write it as shown on screen. Given 4 power 3 equal to 2 power 2 whole power 3. By solving, we get 64 equal to 2 power 6. Therefore, its logarithmic form is log 64 to the base equal to 6.
Let us solve a few exercise problems. Click the tab to view solution.
Knowledge check. Attempt the following questions to check your understanding. Applications of real numbers and logarithms. Application of real numbers. Real numbers helps us to count and measure quantities of different items. You dial real numbers in your mobile phone to call a friend. Real numbers can be thought of as points on an infinitely long line called the number line or real line. In the physical sciences, most physical constants such as the universal gravitational constant and physical variables such as position, mass, speed and electric charge are modeled using real numbers. The intensity of earthquake is determined by using logarithms. An instrument called the Richter scale is used to determine this intensity. Measuring acidity using the pH scale or concentration of ions involves logarithms. Try to solve the problems in the practice zone on your own. Summary. Let us recap the highlights of this chapter. The fundamental theorem of arithmetic states that every composite number can be expressed or factorized as a product of powers of primes, and this factorization is unique apart from the order in which the prime factors occur. Let x be a rational number whose decimal expansion is terminating. Then x can be expressed in the form p by q, where p, q are co-prime, and the prime factorization of q is of the form 2 power n, 5 power m, where n, m are non-negative integers. Let x is equal to p by q be a rational number, such that the prime factorization of q is of the form 2 power n, 5 power m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. Let x is equal to p by q be a rational number, such that the prime factorization of q is not of the form 2 power n, 5 power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating, or recurring. The square root of any whole number is either a whole number or an irrational number. If p is a prime number and p divides a square, then p divides a, where a is a positive integer. If a power n is equal to x, then logarithmic form of it is log x to the base a is equal to n, where a not equal to 1. The three laws of logarithms are: log xy to the base a is equal to log x to the base a plus log y to the base a. Log x by y to the base a is equal to log x to the base a minus log y to the base a. Log x power m to the base a is equal to m log x to the base a. Let us list out the formulas used in this chapter. The three laws of logarithms are: log xy to the base a is equal to log x to the base a plus log y to the base a. Log x by y to the base a is equal to log x to the base a minus log y to the base a. Log x power m to the base a is equal to m log x to the base a. Follow-up work. Examine each of the following as rational or irrational. Find the HCF of 16 and 40 by prime factorization method. Hence find their LCM. State whether the following rational numbers are terminating decimals or a non-terminating, repeating decimals. Prove that 3 plus 2 root 5 is irrational. Expand log root x cube by y square. Determine the value of log root x to the base x. Write 27 to the power 2 by 3 is equal to 9 in logarithmic form. Write log 8 to the base 4 is equal to x in exponential form. Test your understanding of the chapter by taking the mock unit test. You have successfully completed the chapter Real Numbers.